everyone. My name is Yaira, and I'm going to be your moderator for this session. For this session, our speakers are Paul Chau and Cora Howell, and they are presenting on the Ouroboros effect, the mathematical models of AI self-training collapse.
Hello, everyone. I hope everyone's enjoying the conference and the weekend so far. I'm Cadet Paul Chau. I'm co-presenting with Cadet Cora Howell. Both of us attend the United States Military Academy at West Point, and we completed this project as part of SCUDEM 2025, answering prompt B. So we're just here to share the model that we developed, and we're actually trying to turn this project into a publication in the Rose-Hulman Undergraduate Journal of Mathematics. So we would especially welcome any feedback or ideas that you may have on our models.
So, as artificial intelligence systems are increasingly being trained on synthetic data that is generated by other AI systems, it leads to model collapse. Recent research by Ilya Shumilyov and colleagues shows that recursive training causes the tails of the distribution to disappear. This means that rare, unique outputs slowly vanish. Our project asks if we can model this collapse mathematically, and in this literature, model collapse is formally defined. It demonstrates when AI systems are recursively trained that outputs by earlier AI models, the tails of the data distribution begins to disappear. So in other words, the rare or outlier examples become underrepresented with each generation of retraining, and over time, the variance in the data set is reduced. Eventually, the model will drift towards a delta function and a single point distribution where the diversity in the outputs essentially vanishes, and this is the phenomenon we refer to as model collapse. So based on that literature, we structured our project around three central research questions. First, in a completely closed system where AI only trains on its own outputs, does the model quality of the system decline dramatically, gradually, or not at all? Second, if we introduce a human-generated data set into the system, can that slow, stop, or even reverse collapse? And third, what happens when multiple AI systems interact and train off of one another's outputs? These questions guided the structure of our mathematical modeling and allowed us to compare three progressively more complex systems. So to model this collapse, mathematically, we use three differential equation models. We focus on two key parameters, the mean and the variance. Variance reflects diversity in outputs, and the mean relates to overall performance. We measured perplexity as used in the literature. The three models were a fully self-trained system, a system with human input, and a system where two AIs interact. Each model modifies how the mean and the variance evolve across generations. And so our first model, we analyze a fully self-trained AI system, meaning it only trains on its outputs with no human input. For our models, we assume that all data follows a normal distribution, and therefore we're able to play around with the parameters of the Gaussian distribution, such as standard deviation and mean. If we assume that all data follows this Gaussian distribution, we can model how the mean and variance evolve across generations. Our dependent variable was perplexity, which is the same variable that the literature itself followed. And in our model, variance represents diversity in outputs. The mean reflects overall model performance, which is measured through perplexity, which quantifies how surprised an AI model is by new data. A low value means it predicts well, and a high value means it's more confused or inconsistent. So we are able to derive a differential equation where variance decays proportionally to itself, which we eventually solve. Here are the core differential equations for our closed system. Equation 1 describes how the variance of the data distribution exponentially decreases across generations. The higher value of gamma, the faster the collapse of this happens. And the first equation also shows that variance decreases proportionally to itself. Because it's proportional decay, this produces exponential decline. The second equation describes how the mean of the distribution can drift less as variance shrinks. The mu minus 1 divided by mu term ensures that the perplexity itself can never fall below 0. And as variance shrinks, the mean is pulled downward, and the parameter alpha controls how quickly that occurs. Together, these equations describe a system where diversity and performance both deteriorate over time with no corrective force. So the first differential equation we solve using separation of variables, and the second one we solve numerically using MATLAB's ODE45 solver. The initial conditions and parameters that are shown at the bottom of the screen were arbitrarily assigned based off of a possible data set, and the graph illustrates that the mean perplexity and variance decrease exponentially across generation. And so when we solve the variance differential equation, we obtain a exponential decay function. This lets us calculate a specific collapse time. This is important because it transforms the idea of collapse from something abstract into something measurable, and we show that this occurs roughly at 230 generations. So we can estimate precisely when a closed AI system can lose its meaningful diversity. And ultimately, this means that we could predict how long a closed AI system can remain viable.
So to answer our second research question, with that being the effects of incorporating human data within an AI data training set, we create the second model here. So essentially what it looks like is that we introduce these new terms into our differential equations. So it's essentially the same exponential decay model that you saw in the earlier two equations, except now you have these parameters rho here, which basically says how much human data are you going to fix in each training generation? Are you going to keep, are you going to ensure that 5% of the data set is from a human source? Are you going to ensure 10% of the data is from a human source? So that's something that you can arbitrarily assign. And from that, we can solve those differential equations to see its effects. So here we show you how we solve for them. And something neat about this is that you're able to solve, since we assume that all the data follows a Gaussian distribution, you're able to solve for standard deviation and mean, so such that you're able to solve for a steady state solution. So you're able to see at what mean and standard deviation the data set will eventually converge to after enough generations if you keep a fixed amount of human data in each training generation. So graphically, that looks something like this. So in the top left, you'll see with no human data, you see that collapse in the yellow to a delta function like we saw in the previous model. But with increasing proportions of quote unquote human data, you see that there's less and less divergence from the original data set. And eventually, if you see rho equals 1, you basically see no difference between the original and the 120th generation model, which makes sense. So basically, what this is indicating is that with greater amounts of data that you preserve to be human, then you have a closer and closer originality with your original data set. To answer the third question that we proposed, talking about what occurs if multiple AI models interact with each other. Again, we have the same baseline exponential models that we had, but now was introducing another term, kappa. So kappa is the rate of synchronization. It's a parameter that basically measures how strongly two AI models are pulled to one another. Manipulating again the same fundamental Gaussian parameters of standard deviation and mean to essentially see how they interact for different values of kappa. So again, graphically, it looks something like this. So with a kappa of 0, which essentially means that the two AI data sets have no pull on one another. They have no strength on one another. We see that they remain, relatively divergent across a numerous amount of generations. But for increasing values of kappa, for increasing values of the parameter, you eventually see, for example, kappa equals 0.04 in the bottom middle there. You see that the dotted line and the solid lines become closer and closer together, which will lead us to conclude that after enough generations, those two AI datasets will become indistinguishable from one another. So that brings us to our conclusions and key takeaways from the model. So our 3 research questions. So 1, in a closed system, will the quality of the AI model dramatically decline, slowly decline, or remain unaffected? As you saw, the rate of decline depends on how strong the parameters are defined, and it depends on what data set you're working with. But no matter what the parameters are, you will be able to solve for how many generations it would take for a model to collapse. That was a logarithmic expression that you saw on model 1. For the second question, in terms of human data, so if you have any amount of human data, whether it be 1% or 5%, eventually you will reach a steady state solution where the model is no longer changing after subsequent generations. And then for our third research question, the role of multiple AIs coupling and interacting with each other, the conclusion we reach is that after enough generations, the two data sets will become indistinguishable from one another. So some implications on that, data integrity is a central component of any data system, especially with AI. If you refer back to the original literature that inspired this whole project, the concern was that data would eventually be lost because the tails of data distributions would be lost because AI samples wouldn't take them into consideration. So for each one of our research questions, we come to a different consideration. So in the closed system where the AI has no interaction with human data or other AI systems, data preservation is a matter of knowing how long it takes for that model to reach a threshold of data loss that's no longer tolerable. So for example, if you sent a satellite into space that had no interaction with the outside environment and was completely self-contained, right? How long before that AI program in the satellite was unable to recognize certain things because of that convergence to a delta function? In terms of a system with human input, suppose that you have a factory with an automated control system. How often would a human supervisor have to come in and check off the work of the AI, right? And in terms of AI systems, what conclusions lead us to think is, suppose you have two AIs interacting with each other, and one of them is a teacher model, one of them is a student model. How long before the teacher and student model become inseparable, indistinguishable from one another? So these are just the natural implications that follow from our conclusions. But of course, we're limited by the fact that our proposed model is only based off what we saw in preliminary literature. And the next steps for this research would be to fit it to an actual data set and see what arises from that. Now we want to take a couple minutes. Coral and I, both of us are from undergraduate. I'm a sophomore, she's a freshman. So we're relatively new to this game. So we just want to take a few minutes to talk about the educational value SCUDEM and Samode brought to us. I'll go ahead and start off. So I'm a chemical engineer, and basically all my classes revolve around modeling. So taking processes, taking really big picture ideas and translating them into mathematical equations and expressions. And I didn't realize this. This is my second year doing SCUDEM, but I didn't realize that I got really good at doing that because of the type of stuff that we do during SCUDEM during this competition. I'm also a pre-medical student. So I take a lot of biology classes. I just happen to see there's a lot of overlap between being able to think about complex systems and trying to express them in another way. I think it applies to all disciplines. I think it's helped me out in all my classes and all my endeavors. Cole, do you want to add anything to that?
Yeah, as a math major, this project helped me learn how to use mathematical tools in more real-world technological problems. It allowed me to model a live issue in artificial intelligence, which helped me strengthen my use of mathematical systems to real-world phenomena.
And I'm sure Cole will talk about this when she's a sophomore, but I was fortunate enough to receive a $15,000 scholarship for my research. And I attribute a lot of my success in my research to the fundamental skills and research experience I got from SCUDEM these last couple of years. Right now, that concludes our presentation, but now we're open to any questions and to reiterate, especially any feedback or ideas that you may have, because we're trying to turn this into a publication. Thank you.